Okay, so today we're going to talk about a new topic. All right, thank you. A new topic. Today we're going to talk about momentum. Yay! I don't think anybody's ever cheered the word momentum before. Okay, so we have an object, right? And we know some things about this object. We know objects have mass, right? We know objects have velocity. These are simple physical things that we can measure, we can observe, we can talk about since the dawn of time, right? Now there are other quantities that we can derive from these quantities, right? So velocity is a vector. We can derive something called momentum, which is just mass times velocity. And then the question is, why do we do this? How is it useful? What does it mean, right? Well, first I want you to remember that momentum is just a derived quantity. Okay? It's just a combination of two things we know. But let's think about how it affects, let's think about how it relates to other things we know. All right, we know that acceleration, for example, is the derivative of velocity with respect to time, right? So if momentum is velocity times mass, then the derivative of momentum with respect to time is mass times the derivative of velocity with respect to time, right? Which is equal to ma, right? So that means that this is equal to force. Okay, so what does that mean? Well, remember we defined this quantity force, and earlier we sort of vaguely associated with acceleration. So forces are things which induce acceleration. It's not very precise. Why isn't it very precise? Because it depends on the mass. If you put the same amount of force on two objects, you don't get the same amount of acceleration because they have different masses, right? F equals ma, the mass is important. Just how, like, remember the monitor example of the Earth. The Earth and the monitor apply the same force to each other. There's very different accelerations because there's different masses. So it's not really fair to say that force is providing an acceleration. Really what force is doing is changing the momentum. Okay? Force is something that changes the momentum of an object. That's the most direct connection between these two concepts. Okay, so both force and momentum are just ways to understand how acceleration and mass and velocity are connected. Okay? And it makes some calculations very easy. And then we're going to make another classic mistake, which is take a word from English that you know and give it a new meaning to confuse you. Okay? So, just like we did with work, right? And then we'll give it a nonsensical letter. Like, why does impulse J? It doesn't make any sense. How should we spell impulse to distinguish it from the English word?
Two O's.
X?
Two O's.
Two O's? Impulse. Okay, I like Jimpulse. That's good. That's clever. Jimpulse. Okay. I like that. Jimpulse. Okay. Now, what is Jimpulse? Jimpulse is change in momentum. Okay? The change in momentum. It's units of momentum. Force is the rate of change of momentum. Jimpulse is the change of momentum. Okay, so you have certain momentum, then you have a new amount, the difference is J. Okay, so let's think about that practically, right? Think about what happens when you have a baseball, right? For example, you're closing out the World Series, and you're throwing the baseball as hard as you can, and you throw it, and while it's in your hand, right, you're throwing the baseball, it travels a certain distance, delta D, and over time, delta T. Okay? Now, you can do work on this baseball, which is the force you apply times the distance, right? You also give this thing some Jimpulse, which is the force times the time. Okay? So the change in momentum is a force applied over a time period. So you can change the momentum quickly by applying a large force over a short time, or you can have the same change of momentum or a slow force over a long time. Right? The pitcher can either just stand there and throw really quickly, or you can like run all the way from center field really slowly, right? And give it the same amount of change of momentum. But of course, the force required to do one is different than the force required to do the other. Okay, so these are just some definitions, right? Just some concepts that we relate to other concepts we already know. Okay, and then we're going to spend the class period getting familiar with these and using them to solve some physical problems. Okay, so let's just do a quick, very simple example, right? So here we have a ball with mass 0.4 kilograms, moving initially to the left at 30 meters per second. So initial velocity is negative 30 meters per second. After it hits a wall, the ball is moving to the right at 20 meters per second. So the ball is coming in like this, at 30 meters per second to the left, and then it leaves at 20 meters per second, should be shorter. And then it leaves at 20 meters per second after hitting the wall, okay? Okay, the question is, what is the impulse on the ball? Vf equals 20 meters per second. What is the impulse? Semicolon?
Yeah, it would be 20 times 0.4 minus negative 30 times 0.4. Well, yeah.
Right, and then it's so it's 20, right? And the units of this are kilograms meters per second, because it's momentum, mass times velocity. See? And here you have to be careful with the signs. The problem actually reads left 30 meters per second and then right at 20 meters per second. If you get confused, you might have thought the difference was just 10, and the difference, of course, is 50. Okay, that's pretty simple. Okay, let's do a clicker question. All right. You're testing a new car using crash test dummies. Consider two ways to slow the car down from 90 kilometers per hour to a complete stop. One, you let it slam into a brick wall. Or two, you let it plow into a giant tub of Jell-O so it comes to a gradual halt. Okay? In which case is there a greater impulse of the net force on the car? Not a tricky question, okay? Not supposed to be tricky. Just testing your understanding of these definitions we've given you. Okay? Everybody click in. We got 41. All right. So the question asks for the impulse. What is impulse? Change of momentum. Initial momentum is what? Its mass times its initial velocity. Final momentum is 0. Does it matter how quickly you slowed it down to 0 if you're just calculating the initial and final momentum? No. And the impulse only depends on the initial and final momentum, right? Not on how long it takes. So the answer is C. Right? Questions about that? Okay. Then, same question, but now it's asking, in which case is there a greater force on the car? At any moment, an instantaneous force on the car. Are they the same, greater, equal, what?
Yeah.
Okay, you guys figured this one out? Right? So if you're going to change the momentum in the same amount of time, you need a larger force, right? Okay. Okay, now if there is, say you have a system, right? And you have some system of something. Say, for example, the system is two people skating on the ice. Okay? And it's romantic, so they're holding hands. What's funny about romance, huh? That makes you laugh. Yeah? Okay, so they're skating, right? They're holding hands. Now, if there's no external force on them, right? There's no wind, gravity's balanced by the normal force. If there's no net external force on them, well, that's right. It's a new symbol, yeah. Okay, if there's no net force on this guy, right, then there's no acceleration, right? Which means there's no change in momentum. Which means momentum is conserved for this system, right? Okay, so that's cool. That means that no matter what these two do to each other inside the system, right, spin around, hold hands, not hold hands, punch each other, whatever, there's no change in momentum on the total system, okay? So this is something we call like an external force. Something acting on the system. And the system is just something we define, right? External, internal is just a question of definition of the threshold of your system. Right? Now, if there can be a force from one person onto the other, right? Force. There can be a net force on the girl. If he's pulling or pushing or whatever, or gives her something, for example, there can be a net force on her, right? Which is not zero, which means that she can change her momentum, right? And that makes sense. If he pushes her, or she pushes him, or whatever, then one of them is going to move that changes their momentum. But the whole system doesn't change its momentum no matter what they do internally. Okay, so I'm not saying anything more complicated than if you draw a dotted line around some objects and call that a system, and there are no net forces on it, it's not going to change its momentum as a system. Now, internally, crazy stuff can be happening, right? But as a system, it's not going to change its total momentum. Okay? All right, one other thing we should know about momentum is, of course, it's a vector, right? So it has components. You need to think about it in terms of x and y. So for example, if you have particle A and it has some momentum up, call it dA, and you have particle B and it has a momentum orthogonal to that, right? Here's a system with two particles with two different momentum, right? The total momentum of the system is the vector sum of these guys, right? Not the linear sum. You can't say that the magnitude of momentum is equal to the magnitude of this momentum plus the magnitude of the other momentum, all right? This is not true. Okay, so these are vector quantities, you have to add them like vectors. So you want to say, what's the momentum of the system A plus B? Well, it's going up and to the right, so it has an angle. Right? You have to add them like vectors. Either components, or you can do it graphically, right? Okay, so let's think about a more realistic case, right? Let's think about what happens if you have a rifle, okay, and it's got a bullet inside, okay, and before you shoot, the system has no momentum, right? It's just at rest. Now, right, so the initial state, V bullet equals V rifle equals 0. Now you pull the trigger, explosion happens here, bullet goes this way, right? So now if the mass of the rifle is 3 kilograms and the mass of the bullet is 5 grams. Notice the difference in units there. Right? In the final state, if we're told that the velocity of the bullet is 300 meters per second, right, then what do we know about the velocity of the rifle? Well, as a system, the bullet plus rifle have no net forces on them, right? So what does that tell us? The momentum of the bullet plus rifle system is conserved, right? So P initial equals P final. What is P initial? 0, right? Everybody's at rest. What's P final? Well, it's it's 0, but MBVB plus MRVR, right? It's equal to 0. So velocity of the rifle is MBVB over MR, right? Negative. So what does this tell us? Well, first of all, they have opposite velocities. That makes sense. In order to have totally net 0 momentum, it has to be going in different directions, right? So one velocity is the opposite of the other one. Let's think about their ratio. The velocity of the rifle is related to the velocity of the bullet by this ratio of the mass of the bullet over the mass of the rifle. Right? If this is well designed, the bullet is very light and the gun is fairly heavy, the bullet is going a lot faster than the rifle. Right? If your rifle was as light as your bullet, what would happen? Yeah, it'd be going right back at you just as fast as the bullet is going forwards, right? Okay, so. However, even if the rifle is going slowly, that doesn't mean it does not impart a lot of momentum, right? And this is what's known as the recoil, right? So, now how does a bullet hurt you? A bullet hurts you because it hits you and imparts momentum on you, right? The gun going the opposite direction is giving exactly the same amount of momentum as the bullet that you're firing. Now let's think about collisions. Okay. Imagine we have 2 gliders on a frictionless surface. Okay. And initially, this guy is 2 meters per second. Right. And this one, VB, is negative 2 meters per second. Is this too small? Can you guys see this back there? Yeah. It's okay. Yes, it's too small. All right. And then they collide, right? Okay, and we put some little springs here. Okay, and then after the collision, they go their separate ways. Okay? And then we're asked, what is the velocity of this guy after the collision? And we're told, let's see the relative masses. MA is 0.5 kilograms, MB is 0.3 kilograms, so they're not equal. And we're told this, that the final velocity here is 2 meters per second. So how do we figure out what the final velocity of A is? Well, are there any net forces on this system? No, so we can use conservation of momentum, right? And so we can say initial momentum is final momentum, so MAVA initial plus MBVB initial is equal to MAVA final plus MBVB final. Right? And what do we know in this equation? We know the complete initial state. We know the masses and the velocities of both gliders. We know the masses in the final state, of course, and we know this one, VBF, that was given. So we have an equation with just a single unknown. So we can just use conservation momentum to solve this one trivially, right? Okay, what if this wasn't given to us? And we were asked to find both. Now we have one equation with two unknowns. Energy is conserved. How do we know energy is conserved?
Because there is no friction.
There's no friction in the system, right? And these guys have springs, so we can use these guys as little rigid guys. There's no like crazy interaction that happens, no compression, no crushing, no weird things, right? All their kinetic energy is turned into potential energy of the spring, and then back into their kinetic energy. So we can use conservation of energy, exactly. So first we use momentum, and then we can also use energy. Right? And so how do we use energy? Well, it's just the sum of the kinetic energy in the initial state, VBI, is the sum of the kinetic energy of the final state. VBF squared. All right, so this gives us two equations and two unknowns. Thank you. Two equations and two unknowns. Not pretty to solve because you have these squared terms, but it's certainly doable. Okay, so in these cases when there's conservation of energy, we'll talk about that a little more in a minute, you can use conservation of momentum and energy to get your two equations. Okay, now we've been thinking about these in one dimension. How do things change in two dimensions? Well, like I've been saying all quarter, two-dimensional problem is just two one-dimensional problems. And it's important not to confuse yourself and try to think about a two-dimensional problem all at once sometimes. All right, so let's say you have some object here, and it's being shot at a target. Okay, and the target is some funny shape or something. So this is A and this is B. So we have initial velocity of A, and then afterwards, these guys come off at some angles. Alpha and beta. Okay, so the initial state is like this. The final state is like this. Okay, so, and the question is, for example, what is the velocity of A after the collision? Well, momentum is a vector quantity, and it's conserved separately in every direction. You can't take x momentum and turn it into y momentum. Right? Momentum is conserved in x, and separately, momentum is conserved in y. Which remember, right, F equals ma is a vector equation. Right? F equals ma is really three equations. Right? Fx equals max, Fy equals may, etc., down to z, right? These are separate laws. Similarly, P initial vector equals P final vector are three equations. P initial x equals P initial y, final, getting ahead of myself there. P final x, P initial y is equal to P final y, etc., right? These are separate conservation laws. Okay, so what does that mean? It means you analyze this in terms of its components, applying the conservation momentum separately for each component. So for example, the x component. All right, let's just think about the x component. Well, this guy has initial velocity, right? So MA VAI. This guy has no initial x velocity, right? MAVAF plus MBVBF. Right? In the final state, both of these guys have x velocities. So this x momentum has to get turned into this x momentum and this x momentum. Right? Regardless of what's happening in y. This has to be true. Now in y, what is the initial momentum in y? 0. Right? Which has to also be true in the final states. MA, VA, so I guess I should have an x here and here. AFY plus NB, VBFY, right? And since masses have to be positive, that means that these two guys' velocities have to have opposite signs in order to give us an answer of 0. Which makes sense, right? That's your intuition. If this guy hits this guy, these guys have to go back to back from each other. Okay, and then if you don't have enough equations, you can apply conservation of energy as well. Remember, energy is a scalar quantity. It doesn't have a direction, so you just get one energy equation. For every dimension you're working in, you get one momentum equation. Okay? Now, when can you apply conservation of energy to a collision? Well, we have two kinds of collisions we talk about in physics. Okay, so in the initial case, you have a particle moving this way and an object moving this way, right? So the initial state, and if the final state is two objects moving out, all right, this is what we think of as an elastic collision. Okay, what does an elastic collision mean? Well, I remember it's elastic because I think about these guys as having little springs on them, so that when they touch, all the energy goes into potential energy of the spring, and then it gets turned back into kinetic energy. This is the kind of collision we've been talking about. We call it an elastic collision. We call it an elastic collision. The objects are not deformed. They don't stick together. There's no chemical reaction. There's no change of internal structure. There's no friction. It's pure. Energy is conserved here. Okay. The kinetic energy of the outgoing products is the same as the kinetic energy of the incoming products. Okay, that seems to make sense, right? Why am I going on and on about that? Well, there's another case, right? If you could have the same initial condition, but instead of having, little springs on there, you could have like little water balloons full of super glue or something, right? So that when they touch, they form one combined object, right? And the direction it's going depends on the net momentum in the initial state. This is something we call an inelastic collision. Okay, the definition of something, an inelastic collision, is that the kinetic energy of the final state is not equal to the kinetic energy of the initial state. Whereas in this case, it is. Okay? So if you're doing a problem and it says an elastic collision, that is an elastic collision, not an inelastic collision. If the collision is elastic, that means you can apply conservation of kinetic energy. Now, do elastic collisions violate the principle of conservation of energy? No, it's just not true that this special subset of energy is conserved, the kinetic energy. Right? So what's happening to the kinetic energy, that's lost here? It could turn into heat if there's friction, or sound, for example, or compression of the objects. There's a lot of ways for it to go. Okay? So let's summarize, because it's important that we understand the difference here. Okay, so momentum, kinetic energy, and total energy. Okay, for the elastic collision and the inelastic. Okay, so help me out here. In the elastic collision case, is momentum conserved? Yes. Is kinetic energy conserved? Yes. Is total energy conserved? Always, right? Okay, in the inelastic case, is momentum conserved?
Yes.
Yes, absolutely. Is kinetic energy conserved? No. Right? And this one is conserved. Okay, so this is the difference. You can always apply conservation of momentum and conservation of total energy. You can't always assume that the kinetic energy is conserved from the initial state to the final state. That's the difference between the initial, that's the difference between the elastic and inelastic collisions. Okay? Okay, so what happens in inelastic collision? So I think this is a terrible question. Why is this a terrible question? Well, in the book, when they address this kind of topic, they assume you only know exactly what they've taught you, and they like to define terms, and then you just believe them and accept them and use them as if they are absolutely true and always applicable. So for example, in the book, the answer would be internal energy, because that's their categorization of it, okay? Because they do not consider the possibility that particles could collide and create mass, which we happen to know is true. Or that other things, that you could turn into other things, like sound. So in the book, they call this internal energy. I think anybody who said depends on the collision is giving a reasonable answer. Anybody who pressed C is just being silly. Okay? The point is the kinetic energy does not disappear. It turns into something else. Internal energy, sound, mass. I guess you could say mass is internal energy. Okay, questions about that? Okay, let's do this one. Two objects with different masses collide and stick to each other. Okay, so they're stuck together. Compared to before the collision, the system of two objects after the collision has what? Okay, so first of all, they didn't tell us whether it's an elastic collision or inelastic. So, how are we going to treat it? Why inelastic? Sorry?
They stick together.
Why does that mean it's inelastic?
Because elastic means when they hit each other and bounce apart, and inelastic means
That's really a semantic answer. Who has a physical explanation for why sticking together means it's inelastic? Remember, what's the critical definition of inelastic? Kinetic energy is not conserved. So can you prove that if the two objects stick together, that kinetic energy is not conserved, even in the absence of any numbers?
maybe.
Who has an argument?
Before they collide, they each have some sort of velocity, and that's equal to 1/2 mv squared. After they collide, the v, because they are going in opposite direction, the v becomes much smaller.
How do you know? How do you know it becomes smaller? Are you saying that it becomes smaller, that implies a loss of kinetic energy? Can you prove that it's the case? You have to use the fact that they stick together. Sorry?
Because the velocity is going to be equal to the total momentum, except it's going to be mass 1 plus mass 2. So therefore, in order to equal the left side of the equation, the velocity is going to have to be less.
Okay, but that doesn't mean that kinetic energy is lost. Imagine the system, imagine you change to a frame when the total initial momentum is 0. Then what's the final momentum? So what's the final velocity? So what's the final kinetic energy? Is the initial kinetic energy 0? So doesn't that prove that kinetic energy decreases? Right? You can't do that if both objects leave, right? You can't make the same arguments because in the final frame there's still kinetic energy. Okay, so the fact that they stick together means that there's a loss of kinetic energy. Does everybody follow that argument? Okay, so now let's get to the question. We know it's inelastic, right, because they stick together. So what does that mean? Let's see. Most people say the same momentum but less kinetic energy because you can read a board of checks and crosses, right? Okay, questions about that? Okay. All right. What if these two objects collide and bounce off each other? All right, so it's an elastic collision, so there's conservation of energy and conservation of kinetic energy. Okay, so no confusion there. Okay, so let's do some examples, work through some problems, see how to apply this stuff to homework-like problems. Okay, so let's take a very simple case to start with. Let's do an inelastic collision where you have some object A moving at 2 meters per second, right, with mass of 0.5 kilograms, and object B moving the other direction, negative 2 meters per second, 0.3 kilograms, okay, and then the final condition is A and B are stuck together. The question is, what is the final velocity? Okay, well, we can use conservation of momentum, right, to say the initial momentum is equal to the final momentum. The initial momentum is the initial mass right, we have two objects, each with mass and velocity. In the final case, we have a single object with mass ma plus mb and a single final velocity. That makes the problem simpler. So you can't use kinetic energy. However, you have one fewer variable, so you don't need kinetic energy. Right? If we had two objects here, we'd have two velocities, we'd have two unknowns. Since we have a single object, we have a single velocity, we have a single unknown, we only need the one equation. So it's very easy to solve for VF here. Right? It's upside down, right? Didn't I get the units wrong? Tell me you've never done that. Okay. All right, let's do a slightly more complicated example. All right, say we're one of the guys in those videos and we're shooting a gun. And we're shooting it at a block suspended by strings. Okay. So here's our bullet. Bullet has the initial velocity, right? So we're given the mass of the bullet and the initial velocity of the bullet, and we know the mass of this wood, right? The bullet buries itself into the wood, and then the question is, how high up does the combined bullet plus block swing, right? So the final state is like this thing. That was a terrible drawing. The rope should not be longer, obviously. They're not springs. Well, that would be crazy, right? A block suspended by springs. Oh, we'll do that in the final, maybe. Joking. Okay. So the question is, what is this change in height? So elastic or inelastic? Inelastic. Okay. So how do we approach this problem? Conservation momentum, which gives us what?
So we get our original momentum of the bullet and find the final momentum of the bullet plus the block, and the energy of that block with the bullet in it, and then becomes
Good. So break into two problems, right? First, find the velocity of the bullet plus wood system, right? You do that using inelastic collisions, right? You exactly just solved that problem. One object hits another one. What's the velocity of the combined system, right? Use conservation momentum to solve that problem. Okay, the second step, once you have the velocity of this thing, it's an energy problem, right? You just say, well, this kinetic energy gets turned into potential energy. I really don't want to have to use circular dynamics and all sorts of crazy stuff. Think about how this thing swings. I'll just use potential energy. Because it doesn't matter how far it swung sideways, the only thing that matters is how high it goes. That's all I need to know. That's all gravity cares about, right? So step 2 is figure out how the kinetic energy gets turned into potential energy, right? So a complex looking problem broken into two rather simple pieces, right? So here, we can say the mass of the block plus the mass of the wood times the final velocity is equal to the bullet mass, bullet velocity plus wood mass plus wood velocity, which is 0. All right, so we just ignore that. All right, so we can get the velocity because it's just the ratio of these masses. It's the velocity of the bullet times mb over mb plus mw. All right, so obviously this is going to be going much slower than the bullet. That makes sense. And as the mass of the wood goes to infinity, this velocity goes to 0, which also makes sense. And as the mass of the wood goes to 0, this thing becomes like an aerogel, then the velocity is the mass of the bullet. Also makes sense, right? It's good sometimes when you get an answer to check the limits, that your expression makes sense in all sorts of extreme conditions when you know what the answer is. Okay. Now we know the kinetic energy because we know the velocity, right? So now can we use kinetic energy here? I mean, I thought this was an inelastic collision. How can we use kinetic energy? Well, we're not using kinetic energy during the collision, right? Now the collision is ancient history. We just have a block of wood with a bullet embedded in it, and we know its kinetic energy because we know its velocity. So we don't care that it was an inelastic collision anymore. We didn't use conservation of energy, of kinetic energy before the collision and after the collision. We're just saying conservation of total energy, right? Kinetic energy initial plus potential energy initial is kinetic energy final plus potential energy final. Remember, you can always use conservation of total energy, right? And if you're worried about, well, this is an inelastic collision, there's some energy loss due to like changing the structure of the wood or something crazy, that's true. But remember, we are considering the stage after the bullet is embedded to when the wood swings up, right? We're not interested in the change in energy from before the collision to after the collision, just from immediately after the collision and before it's swinging to when it's done swinging. Okay, and so here we know the initial kinetic energy. It's 1/2 m wood plus m block times v squared, but this is the same v we solved for after the inelastic collision. The final kinetic energy is 0, right? We call this kinetic energy, this potential energy 0. So we define this height here to be 0 arbitrarily to make our lives easier, right? And then we just need to do m wood plus m block gh. And we know everything in this equation except for our target, which is the height. Okay, so now we're feeling confident, like, yeah, we can handle inelastic collisions. They sound crazy, but we're on top of them. So let's go one step further and think about a 2D inelastic collision. Okay, what happens if instead of getting your nap while you're here in physics class, you're really tired when you go home and you don't notice this truck coming, right? So this one's coming at 10 meters per second. You're here napping at the wheel because you paid attention. You paid attention in physics class rather than taking a nap like your neighbors. And now you're tired. Okay. So what happens here? Well, the truck and the car smooshed together, become some sort of like horrible car-truck hybrid you only see at a monster truck show, right? And this thing has momentum in this direction, right? Okay. It's okay, he's sleeping, don't interrupt him. Okay, so the question is, yeah, he's going to go ahead and say it, right? What is the velocity after the collision? Okay? What is the velocity of the truck plus the car after the collision? Okay, this seems like an ugly problem, right? I mean, it's not just, you know, somebody's hurt, but it seems like a tricky problem. Well, break it down into x and y components, right? That's what we always do in 2D problems. Okay, and it's inelastic, which means all we can do is think about conservation of momentum, right? We can't think about conservation of kinetic energy. We don't know how much energy was lost in the crushing of the car or the airbags or anything like that. So we just use momentum. Now in the x component, let's define our axes, x and y. In the x component, what is the initial momentum? Well, it's just due to the truck, right? The car has no momentum in x before the accident. So it's mass of the truck times velocity of the truck, initial x. Ticks, nice. Okay, and then in the final case, it's the truck plus car system, right, times the final velocity next, right? We know this, we know this, we know this, so boom, we solve for the x velocity of the final x component of the final velocity. Easy. Similarly, the y component has only the mass of the car times the initial velocity of the car in y, right, is the mass of the truck plus the mass of the car times the final velocity in y. Solve that one, right? There you have the velocity vector for the car plus truck combined system. Okay? So a 2D problem looks complicated. Just think about it as two simpler 1D problems. Okay? Questions about that one? I think you should pay attention to physics class, but also try to get home safe, of course. Which means you shouldn't stay up so late playing World of Warcraft or whatever it is people are doing. No, did I guess right or wrong?
League of Legends.
Sorry?
League of Legends.
League of Legends, okay.
Who plays it here?
Nobody plays World of Warcraft anymore?
Yeah.
Old people play World of Warcraft, nice.
Bartenders a lot.
Oh, bartenders, yeah. Old is a relative
I
term.
like playing bartenders.
Okay, let's do some problems from the book. Okay? Here we have an open cart. All right, let's quiet down. An open cart is rolling to the left on a horizontal surface. Okay? A package slides down a chute and lands in the cart. So here we have a chute, a package. Okay? This is a 37-degree angle. This is 4 meters high. A package slides down a chute and lands in the cart. Which quantities have the same value just before and just after the package lands in the cart? Okay, so I was going to do this on a board, but no, it's just a board. I don't want to roll down the slides again. Okay, so let's just think about them. Okay, so in this case here, the question is which quantities have the same value just before and just after the package lands in the cart? Okay. So the package is going to land in the cart. Now, is the horizontal momentum the same before and after? Yes? Question is, which quantities have the same value just before and just after the package lands in the cart? Why?
The momentum of the system or of the cart?
The horizontal component of the total momentum.
So the horizontal component has the same momentum because it's going to be the x component of the x component of the velocity for the box times the mass is going to be the horizontal momentum, and then the same thing with the cart. And then we'll keep the same. You add the momentum, you get the new velocities, and the momentum will stay the same.
So what's the condition under which momentum stays the same?
No external force.
No external force. Is there any force in the x direction here at all? No. So that's conserved. What about in y?
I do not think so. Because,
You sound less hesitant than you intended to be when you raised your hand.
yeah, because when the box drops into the shopping cart, the cart's gonna feel a greater normal force than it usually does, and that normal force will be the impulse that accounts for the block landing in the cart.
Okay, so if we're talking about this system here, right, excluding the Earth from our system, right, then is the y component of momentum going to be the same? Well, what's the y momentum after it drops into the cart? Zero. It was non-zero before, right? Nothing else is any momentum in y. So why isn't there conservation of momentum here?
Because the Earth is
Because we've excluded the Earth from our system, right? If we'd done this, included the Earth in the system, then we would have an inelastic collision problem, where one object is the cart, one object is the box, the other is the Earth including the cart, right? And in reality, when this thing drops on here, the Earth is moved a little bit, right? No big deal. But if you're only considering this, the cart and the box, then the y momentum is not conserved because there is an external force, which is exactly the normal force of the Earth pushing back to avoid getting crushed. Okay? What about the kinetic energy of the cart plus chute? Sorry, package plus cart. No, it's not conserved, right? It's an inelastic collision after all. Right? One's sitting inside the other one, stuck to it now. Okay? Okay, let's do another. Questions about that? Okay. So be careful with how you define your system when you're applying conservation of momentum, right? You need no external forces to have conservation of momentum. Okay, here's a problem from the book. You are standing on a large sheet of frictionless ice and holding a large rock. Okay? How did you get there? You're on some reality show or something. Okay? You're holding a large rock. In order to get off the ice, you throw the rock so it has velocity 12 meters per second and an angle of 35 above the horizontal. Okay? 12 meters per second, 35 degrees above the horizontal. If your mass is 70 kilograms, and the rock's mass is 15 kilograms, the question is, what is your velocity after you throw the rock? So how do we solve this problem? Do you have a refreshing nap? You're awake now? Great. Let us know if that changes. So how do we solve this problem?
We'll break it down.
Okay. Sure. So how do we solve it in each component then?
Well, you want to solve for only really the x component because just like the last problem, the impulse balances the change in velocity.
So we can really think of this as a 1D problem because in Y, you're not going down into the ice, right? So, okay, so it's a one-dimensional problem. Somebody else want to tell me how to set it up?
You find the x component of velocity and the competition, and the attack velocity and whatever your horizontal velocity is.
Yeah, so you say P initial equals P final, right? And P initial is 0. Right, before you throw the rock, it's 0. Right? And P final is your mass times your velocity plus the mass of the rock times the velocity of the rock, right? What's the velocity of the rock? Well, we're told it's, this is 12 meters per second. This is 12 meters per second times cosine of 35 degrees, right? They made this problem unnecessarily tricky. They could have just said, you throw the rock sideways with this velocity, but you know, they gave it an angle. All you need to do is multiply by that angle to bring it back to a one-dimensional problem, right? And so your velocity is going to have to be negative in comparison, right? So then you just solve. It's like a reverse inelastic collision. Okay. All right. Let's do a question. Kinetic energy is not conserved. So what happens to the kinetic energy? What's the initial kinetic energy? And what's the final kinetic energy? Non-zero. What? Where does that come from? Your breakfast, hopefully, right? You ate something, turned it into energy to your muscles, use that to throw the block, right? So you are not just an inert object here, otherwise this would never happen. So you have energy stored in you, right, which is then decreased by throwing this large rock. Okay, next question. 5-gram bullet fired horizontally into a 1.25 kilogram wooden block on a horizontal surface. Okay, bullet into the block. Coefficient of friction between the block and the surface is 0.20. The bullet remains embedded in the block, which slides 0.23 meters along the surface. Okay, we know the mass of the bullet, and we know the mass of the block. Question is, what was the initial speed of the bullet? The bullet initial. So, break it down into steps. How do we solve this problem?
We assume there's no static friction.
We can assume that the velocity of the combined system is sufficient to overcome static friction. Static friction doesn't do any work, right? So how do we, give me the strategy before we solve it.
You go backwards, you have the distance of moves. So you can set, you have the distance of move, you have the friction. Set the work done by friction equal to kinetic energy right after the bullet hits the block.
So use conservation of energy to say the work done by friction has to be equal to the initial kinetic energy of the bullet plus block system, right? Okay, then what does that tell you?
And then once you have the kinetic energy, you can get the velocity. And once you have the
Velocity of what?
Or the velocity of the block plus the bullet.
Okay. So you use the kinetic energy, which is related to the velocity of the block deployed. Okay, then?
And that velocity, you can use that for an inelastic momentum equation.
Right, and then it's just a problem. So you use the friction and work to figure out first you figure out how much work was done by friction. Say that was equal to the kinetic energy of the bullet plus block system, which tells you the velocity of the bullet plus block system. And once you have the velocity of the bullet plus block system, the question is just an inelastic collision question. This thing is embedded in here, initially at rest, you know the final velocity, find the initial velocity, right? Okay, so let's actually do it. Anybody have questions about the strategy? Sometimes when you look at a problem, you can see the strategy. You say, okay, I need to solve this, and then this, and this. Sometimes you don't. In that case, you just start writing down things you know, and hope they come together to give you a solution, right? But it's best if you can try to see the path to the solution from the beginning, okay? So the work done due to friction is mu times the normal force, which is mb plus m of the combined system, right? B plus mb, right? Times g times the distance, right, which is given. So all these numbers we know. So we know how much energy was from friction. We just set that equal to the kinetic energy, mb, right, but this is the velocity of the combined block plus bullet. Right, and we know everything in this equation except for the one term we're looking for, this velocity. Right, so sorry, the mass is canceling. Right, and so there's a mu here. Thanks. Okay, and so I got 9.5 meters per second. So that's how we get the velocity of the bullet plus block system, right? Then we just have an inelastic collision problem. So we say that the initial momentum is equal to the final momentum. You can't use energy anymore because it's inelastic. The initial momentum is the mass of the bullet times the velocity of the bullet initial, which is what we're trying to figure out, right? Is equal to, and there's no initial momentum from the block because it's at rest. The final momentum of the combined object is its mass plus its mass times its velocity, which we just solved for. All right, so now we have an equation where we know everything except for the one thing we want. (229 meters per second). And then again, we can look at this guy and see if it makes sense. Velocity of the bullet and the velocity of the combined system. Say the bullet, say the block has zero mass, right? And this goes away, and the velocity of the combined system is equal to the velocity of the bullet. As this thing, as this mass is very, very heavy, the initial velocity of the bullet has to get larger and larger, right? If the block becomes infinitely heavy, essentially, the bullet has to be going infinitely fast to give it that much velocity. So the answer, I think, makes sense. Questions about that one? All right, let's do one more. Sort of the same style. Okay. 15 kilogram block is attached to a horizontal spring, force constant something. Okay, so we know this force constant, this is 15 kilograms. Okay, it's on a frictionless horizontal table. Suddenly it's struck by a 3 kilogram rock. traveling horizontally at 8 meters per second. The initial rock is 8 meters per second. So traveling horizontally at 8 meters per second, and after the stone hits the rock, it rebounds. The final rock is -2 meters per second. Okay? So it says it's traveling horizontally at 8 meters per second to the right, whereupon the stone rebounds at 2 meters per second to the left. Find the maximum distance that the block will compress the spring. Okay, so then this block is compressed. Find this distance. Okay, so stone hits the block, bounces off, sounds like an elastic collision. The question is, how far does the block move, given that it's attached to a spring? So what's our strategy for this one?
The impulse of the stone is the momentum of the block after the collision. So we find the velocity and therefore kinetic energy of that block, and then we find the
Okay, so we have an elastic collision, right? So we can solve for the velocity of the block, right? Which gives us the kinetic energy of the block. And then you're saying kinetic energy of the block goes into potential energy of the spring, which is dependent on the distance. Seems like a good idea? Okay, so that's exactly right. And we do it just like that. So we say the initial state is the mass of the stone, which we know, times the initial velocity of the stone, is equal to, in the final state, so Pi equals Pf, right? Final velocity of the stone plus the mass of the block times the velocity of the block. And we know this, and this is what we want to find out, right? We want the velocity of the block, right? So velocity of the block is the mass of the stone times final velocity of stone minus the initial velocity of the stone. And this is, as he was saying, this is essentially the impulse, right? It's final momentum minus initial momentum divided by the mass of the block. And this I get to be 2 meters per second. Okay, so we get the velocity of the block, which gives us the kinetic energy of the block, right? And then we have the kinetic energy. Now we're considering now we have a new initial state. Now the initial state is after the block has moved, it has just been hit by the stone, it's starting to move, and the final state is when it's compressed, right? So the initial kinetic energy plus the spring initial energy is the final kinetic energy plus the spring final potential energy. So the final kinetic energy is 0, because we're interested in the time when the block stops moving. That's the maximum compression. The initial compression of the spring is 0, so its initial potential energy is 0. So that means our equation is simple. mv squared equals 1/2 kx squared. So this is the mass of the block, and the stone has bounced off of it. So it's not the combined mass of the stone plus block, just the mass of the block. We know this velocity, we just solved for it. We know what a half is, we know what k is, it was given to us, so we can solve for x. Okay? So you can use energy even in cases of elastic or inelastic collisions if the question is coupled with another question like compressing of a spring. Okay? That's it for today.